let's try to expand a concept that we know from one setting and apply it to a new one, a different structure, a different perspective on it. So we can usually quickly say whether something that's linear, like an array or a list, is sorted. We have clear criteria for what sorted means in those settings. We don't necessarily have that clear of criteria for a tree to fit the concept of being sorted. And so what I want you to do is to take some time to think about this tree that's shown here and whether it fits the definition of being sorted, or more specifically, in which ways can it fit that definition of being sorted that you have, and in which ways does it have features that don't quite fit the definition of being sorted. So pause the video, take a moment, think about those features of what sorted means and how they might apply or not apply to this tree, and then I'll discuss a little. All right, so it's pretty easy to make an argument that yes, it does have some features that we would expect of sorted data. For example, the locations of things fit some criteria of what we would expect from sorted things, namely that lower values are on the left and or are further left, and higher values are further right. So if you look visually, that's generally true. Lower values are over here on the left side of things, and higher values are over here on the right side of things, and the further right I go, the higher of values I see. So it does fit that piece of what being sorted means. There's at least one way in which it doesn't fit well for what we would expect from sorted data, and that has to do with the sequence of how we can get to things. If you remember that in a tree, you always have to start at the root, then we don't get the feature that we would expect of a sorted array, for example, that the first item we access is the lowest value. So no, because the first item to access, the root, is not the lowest value. We can even see if we look closely here that the lowest value is the one that's the furthest to the left. The most steps towards the left takes us to the lowest value, and the most steps towards the right takes us to the highest value. This leads us to another side issue on this, that it's not clear exactly how we would progress from the lowest value to the highest value in a tree. You might start to formulate some ideas, but it can be a bit complicated. It's certainly harder than I equals 0, I plus plus, to get the next highest value and the next highest and next highest. So it's not as clear how to iterate from lowest to highest like we would expect in something like an array. But what we'll find is that this piece of being sorted, the locations of values, and the way that this tree is arranged is enough to get us a behavior that we really often want, and that is fast search, being able to get performance like binary search. And so this kind of tree is referred to as a binary search tree, and it has one very important feature, that all values to the left of a given node, we'll call that node n, of node n are less than n's value, and all values to the right of n are greater than n's value. To the right of n are greater than n's value. And I said this to a general node n because it must be true anywhere in the tree. You can see that it's true of the root here, for instance. And so that the 30 is in the middle, and all values left of 30 are less than 30, and all values right of 30 are greater than 30, and it's true at every other node. If it has children, this is true of it. Its left items are less than it, and its right items are greater than it. And in fact, this has to be true because what the binary search tree gives us is the same ability as binary search to make quick decisions. Just as in binary search, we made the decision of, should I look at the lower half of the list or the higher half of the list or half of the array? The same is what we're able to do here. When I look for a number like 20, I can ask, is it less than or greater than 30? Well, it's less than 30, so we go to the left of 30. Is it less than or greater than 10? It's greater than, so we go to the right of 10. Then we go to the left of 23, because it's less than 23, and there we find 20. So in only a few decisions, I've looked through all of this decent-sized amount of data. I can even do the same for things that are not there to discover that they're not there. For instance, if I were looking for the number 42, I would know that it should be right of 30, left of 62, left of 45, and right of 37. Since it's not there and nothing is there, then I know that 42 is not in this tree, and I've discovered that with only a few checks, a few comparisons. If I did not have that feature of the binary search tree to be true at every single node, then I would make one of those decisions and I'd end up in the wrong place. If I had values that were greater than 45 on the left of 45, then when I made the decision to look right of 45 to find something, I would miss it because it would not be in the right location according to this rule. So this simple yes-no question, or greater than, less than question, allows us to go in a direction and be confident that the only places we need to be looking are in that direction. And so you'll explore a little more on this, thinking about these binary search trees, what are important features of them, and how, more practically, they give us the behavior and the performance we want for today. And in the future, we'll dig more into building them and some of the pieces of that. But for now, you will take a look at some of the features, the structures, the behavior of a binary search tree as you look at Part A of the BST activity.